Hi, welcome back to the channel. In the previous video, you saw how we give coordinates to objects in the sky. In particular, the example was, suppose you saw a comet up there and you wanted to tell your friend, hey, there's a comet up there in the sky, and you want to tell where to look. How do we give coordinates? And we saw that there's a simple way. We specify where an object is on the sky by giving an altitude, how high it is, and an azimuth. That is, we select a stipulated direction of north and how far do we have to move on from that stipulated direction on the horizon. So that gave us the altitude and azimuth coordinate system. So therefore, what it shows is that the sky is some sort of a sphere, and we are looking at angles on the sky. Our eyes are not really sensitive to the distances to these objects, so therefore everything is projected onto this sphere. Since it's a sphere, we are looking at angles. When lines meet, they make a triangle. So if you have three lines meeting, three curves which meet, they will make a triangle. So this is something which is triangle on a sphere. And since they're different from triangles which you draw on a piece of paper, we need to do a different kind of trigonometry to solve such triangles, and that is why what we need in positional astronomy is spherical trigonometry. So that is what we'll look at today. So what really is an angle? Let's first talk about angles, which the way we already know them, the way we draw them on a sheet of paper. So basically you just take two lines, they could be of unequal lengths. Then if you want to draw an angle, the angles are basically, if you draw a circle to make the two lines equal, then the angle is basically an arc which tells you what is the angular separation between the two lines. So the arcs here are given by the two arcs in pink, and you can see that the angular separation is the same between the two curves no matter what is the radius of the circle. So the angular separation in degrees for both the curves is the same. It does not depend on the radius of the circle. So now how do you have a triangle? Well, you take 3 points and join them with 3 lines, and then automatically by the same logic you have 3 circles at the 3 vertices, and therefore you have the 3 angles, and the sum of 3 angles in this particular case is 180 degrees. How do you get that? Well, it's a simple way to check it out. So we'll take the yellow one over there and we'll translate the magenta angle upward, so that goes in there, and the remaining one will take the green and also take it on to that particular vertex. So the moment we take it there, we see that all the 3 angles add up. So the sum of angles is 180 degrees in when you do it that on a plain sheet of paper. That's a plain trigonometry. But this is not the case when you have triangles on a sphere, as we'll see. So how do we have triangles on a sphere? Well, we'll take the same thing. Now we are working on a sphere. Since we're working on a sphere, we have a center of a sphere over here, which is O. So this you could see either as if, suppose you're looking at the sphere from the top. So this is the diameter of the sphere, and the diameter of the sphere is something which is called the great circle. But of course, if you're not viewing it from the top, let's say you're viewing it from the side, then this is also a great circle. Okay? So then P and P prime are what are called poles of the arc, which we have drawn here, the great circle. So PAP prime is also a great circle, and the arc which we have drawn here is also a great circle. So, but however, what is a great circle? A great circle is the one if you take a sphere and you take a plane which intersects the sphere. If that plane passes through the center of the sphere, then the intersection of the plane and the sphere forms a great circle. If the plane does not pass through the center of the sphere, as it, for example, which is there for these green lines, then these green lines or curves are not great circles. They are what are called short circles, but for a great circle, the plane has to pass through the center of the sphere, which is the case for this one. So if I take any point B on this great circle, you automatically see that you have an arc AB, which is part of the great circle. So AB is also a great circle. We call the arc as well as the great circles both the great circles themselves. So it's the same nomenclature. Now you see there's an angle which is made by this arc AB, which is it subtends an angle at the center of the sphere, angle AOB. If the radius of the sphere is unity, then this angle AOB is same as the arc AB. So the arcs on the great circle on the sphere are also angles. A spherical angle is therefore an angle between two great circles or its arcs. So here, for example, you have one great circle which is PAP prime, and then there's the other great circle. Let's say if I draw another one here. So I have two great circles, PAP prime and PBP prime. Then the arc AB is the angle between two great circles. And in fact, it is also making a spherical triangle because you have three vertices PAP. So we therefore have a triangle PAP, which is made from all the arcs of all the sides of the spherical triangle are actually great circles. So the first side is AB, it is part of this particular great circle. Then the second side is PB, it is part of the great circle PBP prime. And then the third side is PA, which is part of PAP prime great circle. So spherical triangle is always made by great circles. Let's make another one, take another example. So let me draw another great circle which passes through B, D and C. So now we have another triangle which is formed by AB, BD and DA. This is different from the original triangle which we formed last time in the previous slide. This was AB, BP, PA. The arc AB is common between both the triangles. So triangle formed by arcs AD gives you a spherical angle AOD, which is subtended at the center. AB is same as the angle AOB, subtended at the center, and BD is the angle BOD, also subtended at the center. So the arcs and the angles are the same because we have taken the radius of the sphere to be unity. So then we form a spherical triangle. For example, this is DAB. It is customary to label the arcs by lowercase letter of the opposite vertex. So we have an arc AD here. It is labeled as B. Arc AB is labeled as D, opposite to vertex D. Arc DB is labeled A, opposite to vertex A. So note that we have now two types of angles. One angle is given by the arc itself because the arc itself is an angle which is subtended at the center. Then there are also angles between the arcs. So for example, at these vertices. So you have an angle D at the vertex D, angle A at vertex A, angle B at vertex B. What are these angles? Suppose you draw at D, you draw two tangents. One is the tangent to arc small a and the other one is tangent to arc small b. Then capital D is the angle between those two tangents. So spherical trigonometry allows finding the relation between the angles between the arcs and the arcs, which are angles themselves. And in this case, the sum of three angles can be greater than 180 degrees. So these are the tangents, and as I said, the angle between the tangents is capital D. When is this capital D, the angle between the tangents, equal to the small d, the arc AB? That happens when the angles B and A would be 90 degrees, or capital D would be the pole of great circle AB. When you have these 90 degrees, then the tangents will be parallel to the line joining B and A to the center. And this is exactly what we were doing when we were looking at altitude and azimuth system. For example, this was what we had there. We had an observer at the center, and north was the stipulated direction from where azimuth begins, and then we had east, west and south accordingly, and then there was an elevation. So therefore, if you have a star at a given elevation, then you had the altitude which was given by the height h, azimuth is given by a, and zenith angle is given by 90 minus h. What is the angle from the zenith? So now you see all these angles are actually angles on a sphere. So let's take a look at revise spherical trigonometry again. So what we had is that there is a great circle. It's an intersection of a sphere and a plane that contains the center of a sphere. Is the shortest distance between 2 points on the surface of a sphere. It's an arc of a great circle connecting 2 points. For example, you have EAB. So the arc connecting the 2 points, it's a great circle. It passes through the plane passes through the center of the sphere. QOP is the diameter of the sphere, is perpendicular to plane of EAB. That is QOP. Then Q and P are basically the poles of A and AB. P and Q are poles of the great circle, and then if we make a small circle which is parallel to AB, so a small circle which is CD, which is made parallel to AB, then P and Q are also poles of the smaller circle. And by construction, if R is the point directly above O on this diameter QOP, then by construction OP is also perpendicular to the plane, because this is a plane of parallel to the great circle. This is like plane of parallel latitude or altitude. So PCAQ is a great circle passing through poles P and Q and intersecting FCD and EAB at C and A respectively. You have the another great circle which is PCAQ. This is another great circle which has been drawn in magenta, and it intersects the smaller circle at C and the great circle at A. So similarly, PDB is another great circle which intersects the smaller circle at D and greater circle at B. So therefore, a great circle, as I said, is equal same as any portion of its circumference. So if you take AB, that is also what we call as the great circle. The arc is the same. The spherical angle between two great circles is the angle between the planes or the angle between the straight lines tangent to the two great circle arcs at either of their points of intersection. So for example, PA and PB. So PA and PB are the two great circles. Their tangents are PS and PT. The angle between them is the angle which is subtended by AB at the center O. So this is the angle AOB or arc AB if the radius of the sphere is unity. A spherical triangle on a surface of a sphere is one whose sides are all segments of great circles. Since the sides of a spherical triangle are arcs, the sides can be measured in angular measure, or that is radians or degrees. That is, arcs are themselves angles rather than a linear measure. So for example, if you have AXY is another one which is drawn over here, another triangle. So you label them by the vertices A, X, Y, and they are made, all the three sides are great circles AX, XY and AY. And since the radius is unity, this is same as the angle they're equal, the arcs are equal to the angle which they subtend at the origin O, the center of the sphere. So AY is same as the angle which subtended at AOY. And then, as I said, you also have the angles between the arcs themselves. Those are given by, if you draw tangents to the 2 points, so you will have therefore angle between the arcs. So since AY is part of the great circle, it's a particular, the whole great circle is this full circumference. If AY is, for example, 1/8 of the circumference, complete circle, then since we know that the full circumference is 2 pi r, then AY is essentially pi by 4 in radians or 45 degrees. Again, this is true because we have taken the radius of the sphere to be unity. Now you may ask why a spherical triangle is made only by great circles. The sides should be great circles and not a small circle. The answer is simple, because the understanding that we have achieved, that the radius of the sphere is unity and then the angles are the same, can only be done for great circles. If you take a smaller circle, then if you take the segment of a smaller circle, which is CD, CD is subtending the angle at center, not at O but at R. So arc CD is not related to the radius of the circle itself, but you can show that CD is AB times sine PC or AB times cos AC. So therefore shorter circles do not make spherical triangles. It is only the great circles which make them spherical triangles. Now there are two useful identities which are often useful because we want to relate the angles between the arcs and the arcs themselves. So these are the two. There are many identities, but there are two useful ones. First one is called law of cosines, which basically relates the cosine of the arc with the cosines of the other arcs and the cosine of the angle of the vertex. You could also invert this and get the cosine of the vertex in terms of the other angles and the cosine of the arc. And then you have the law of the sines, which basically says the ratio of the sine of the arc to the sine of the opposite angle is the same for all the three vertices and the three arcs. I will not prove this for you, but I'll just mention how do you go proving these identities. So basically you start with an arbitrary spherical triangle on a sphere, which is A, B, C taken here with vertices A, B, C, and you know again the angles at the vertices would be A, capital B and C. Opposite to those vertices are the arcs small a, small b, small c. We want to relate these with each other to get those identities. So how do you do that? You first set up a coordinate system from the center of the sphere O with A at the pole. So I have set O as a center and the coordinate system is x, y, z. So z therefore is, because this just the great circle is directly, the pole is above z. So A is the pole and AB I have taken to be on the xz plane. So this AB arc is on the xz plane. In this coordinate system, you specify what are the coordinates of C. Using these angles, you can tell what are the coordinates of C. Use spherical polar coordinates. And then you rotate the xz plane to x prime z prime. So I've rotated the xz plane around about the y-axis. So you rotate this plane about the y-axis. So y-axis remains the same, but x goes to x prime, z goes to z prime. How much do you rotate? You rotate it by angle C, this arc. So that at first you had A at the pole, now B will be the pole. Now again in this new coordinate system, you find what are the coordinates of C. They will be related to the older one by a rotation through an angle C. When you relate the two coordinates through this rotation matrix, you will basically get the law of cosines and law of sines from there. So I will leave it as an exercise for you to do. See you in the next video next time.